Okay, kids, so we're back, section 4.4, the law of conservation of energy. And we've seen some of this in 3U from last year. And we had this equation right here that the total mechanical energy at the beginning of some situation, some change, some motion, total mechanical energy initial is equal to total mechanical energy final. And we kept it pretty simple. It's going to get a little more complicated this year that the total mechanical energy was the sum, right, of the gravitational potential energy and the kinetic energy. So what was the gravitational and kinetic energies sum before and after some change happened, some motion happened? And when we did all of this, we ignored friction and air resistance. And these are called non-conservative forces. We need to step it up a little bit here in grade 12. So we really want to bring friction into the picture. And friction is definitely a non-conservative force. So we need to take a look at this idea of conservative forces versus non-conservative forces. So I'm going to start a table right here. That's what we want to look at now. So conservative forces, gravity is an example. And as you move an object around with conservative forces, uh, as it goes through some type of displacement or change in position, conservative forces like gravity do an amount of work that's independent of path. It depends on an object's properties like mass, for example, and where it is positioned like height. Non-conservative forces, like friction is an example, when these forces act, they usually take any type of energy that may have been around, like gravitational potential energy, kinetic energy. They take those types of energies, right? And they convert it into thermal energy. Things heat up, temperature goes up, sound is made, things like that. And they are most definitely dependent on path. So I'm going to show you an example here to help you understand that. So here's the example. You've got this 1, 2, 3, 4 identical yellow objects. And each time they're going to start at a height initial equal to 0. And they're going to somehow get to here, right? The yellow object eventually will get to up here, okay? And when it gets to there, the yellow object, it's going to have a new height, height final. And we're going to move it in such a way that the acceleration is equal to 0. So it's moving with a constant velocity up here, so there's no real change in kinetic energy. And so how is it moving? Well, there's a constant force F moving this from height initial 0 to height final. Now it's done in 4 different ways. Straight up, very sharp, steep incline, not as sharp incline, and then the shallowest incline of them all. And each of them have a different path length, a displacement change. Because you probably look here, the displacement in the very shallow ramp here, if you would call it a ramp, is much longer than straight up and everything in between. So if you were to calculate the work done by the force, it would be F dot delta D. And we know that in this situation, it would be the magnitude of the force, the magnitude of the displacement times the cosine of the angle between them. But theta here is equal to 0 degrees because the displacement and the force are always in the same direction. So we're reduced to this. But the other thing that's for sure here is if I make this following statement, friction, be it kinetic or static, both, okay? If I say it's 0, as soon as I say that, then I know that the work done by this force is equal to the change in the gravitational potential energy of the object because the mass of the object is always the same. The gravitational potential, the gravitational magnitude of the gravitational field strength is the same. They're all being done on the planet Earth. And the change in height that occurred is the same. So in all of these situations, the work done is the same in all four situations. So what a scientist would say is that the path does not determine, right? The path does not determine the work done. It is independent of path. It's the same work for all of them. Every single situation, the work is the same. And we've seen stuff like this in grade 11. All right. But now in grade 12, we want to add something. We want to add friction, this non-conservative force. And this is where we're going to in the next example. Okay, so let's take a look at the situation now. We're still going to push it up with an acceleration equal to 0. Here's a free body diagram on the object as it's moving from height initial to height final, but now there is friction. So we're going to worry about what's the work done by this applied force F. So what's the work done by that force? Okay. But there is friction, so we're only going to look at these three situations here that are actual ramps. We're not going to look at straight up and down. There's no friction, so there's nothing to discuss involving friction there. So there's the force upward, right? Then, of course, we know there's the normal force, and there would be a force of kinetic friction working against it, and there would be a force of gravity that we would have to break down into components. So I've broken it down into the red component here, which is force of gravity X and force of gravity Y here. Remember, we're kind of using a Cartesian plane where Y hat is perpendicular to the ramp and X hat is parallel to the ramp. So we're using that. And what we're going to do is if we take a look at the free body diagram here, and we're going to assume that acceleration is equal to 0 in these situations, then if we do F net X component, it's going to equal that force F that's being used to push it up, force of kinetic friction, and force of gravity X component, which I have in red there. That's going to be F net. Now, if this object is not accelerating, right, we know that the net force has to be 0 by Newton's second law. And we end up with this, which we then can say that if acceleration is equal to 0, that applied force F has to be equal in magnitude but opposite in direction to the force of gravity X component and the force of kinetic friction. Okay, so we've got the free body diagram on this object here that's being pushed up by the force F. As I said, normal force, force of kinetic friction, force of gravity, divided into two components, our interesting alignment of y hat and x hat. So again, the net force here in this situation, x component net force, is force applied, force kinetic friction, force of gravity, x component, but there's no acceleration. So that's a 0. So we can bring the force of kinetic friction and the force of gravity x component over to the other side, and we end up with this equation right here. Oops, I just erased that. Don't do that. That equation right there. So that's what the force applied is equal to. So if we want to find the work done by that force applied, as always, it's F dot delta D, which is magnitude of that force, magnitude of the displacement, times the cosine of the angle between the force and the displacement. Well, the force is up the ramp and the displacement is up the ramp, so that's cosine of 0. But now I have this that I can substitute in for that force, and that's what I do here. That force's magnitude is now negative. Magnitude of negative force kinetic friction, negative force of gravity x component. And then I'm just going to do some distributive multiplication. Multiply the first term, multiply the second term, and that's what I've done right here. I've multiplied them, and when we do that, we get a sum of the two products. That's what distributive multiplication is. Now we have to take a look at this in greater detail. What is the relationship between the displacement and the height change? Well, let's redraw the triangle. There's the displacement. There's the height change from height initial to height final. So there's our angle theta as ramps are defined. There's your 90 degrees. So opposite over hypotenuse would be delta H over delta D, which would be the sine of that angle. If we rearrange this, we get that delta D is delta H all over sine theta. So I'm going to use that right now. So just bear with me. I'm going to use that right now. Here, I'm going to put in what delta D would be, and it would be delta H all over sine theta. There we have it. Now let's take a closer look at this term right here, force of gravity x component. We're interested in the magnitude really. And we've got theta down here as the ramp angle, which means that would be the complementary angle, so we have to have theta in there. So opposite to theta is the magnitude here, force of gravity x component, all over the hypotenuse, magnitude of the entire force of gravity. So that has to equal sine theta. Well, what would the magnitude of the force of gravity x component equal? Well, it would equal force of gravity sine theta. So I'm going to put that in here. Magnitude of the entire force of gravity sine theta. And look what happens. Look what happens. That cancels out. And I can rewrite it as this. Okay, let's keep going here. Let's keep going. I'm just doing some math here. Well, you know that force of gravity is just mass of the object times the gravitational field strength near the surface of the Earth. Look what I got. I got mg delta H, right? So part of the work that you're doing as you're pushing it up the ramp is changing the gravitational potential energy. That is path independent because you're always gaining the same height. But look at this here. Look at this here. This is going to depend on the path length. This is going to depend on the path length. One ramp is longer than the other. This is why we call it a non-conservative force friction. And that is going to allow us to introduce friction into the law of conservation of energy. And the reason that it allows us to enter friction into the law of conservation of energy is a lot of times this term here is called work thermal. Work thermal. So all the work that you put in as you push something up a ramp, yes, it does change the gravitational potential energy of the object, but friction is also changing some of your energy that you're putting into this as you're pushing the object upward into thermal energy. There's heat production here. So how does this thermal work come into our look at the law of conservation of energy? Well, let's do a grade 11 question. Here's a ramp. We're going to say there's no friction, and the ramp has a certain height y, and an object's going to start here with a velocity initial to 0, and then it's going to slide down to here, and we're going to want to find out, well, how fast is it moving down here? What's its final velocity here? And as it does that, it goes through a path h, and the length, the horizontal length, or the what we call the run of the ramp, is x. So that means we can get all these trigonometric functions for cosine and tan, which I'm sure you understand. Well, if there's no friction, I know the total energy initial is equal to total energy final. Well, at the beginning, it's not moving, so there's no kinetic energy, so it's all gravitational potential energy. So it's just gravitational potential energy initial. When it's at the bottom here, it no longer has any height, but it's moving, so all the energy is kinetic. There's no gravitational. So we end up with this. Mass times g, the scalar version of the gravitational field strength, times y, the height it's falling from, is equal to half the mass times the final velocity, or final speed squared, I should say, as it's at the bottom of the ramp. Well, the masses cancel. I do a little rearranging and I get 2gy is velocity, speed final squared, and then I square root both sides and I get the final speed is root 2gy, and that would have been a really nice grade 11 question. But now I'm going to show you how to do this and use the law of conservation of energy still with friction, and therefore with this work thermal. So now it's different than grade 11 now, okay? We've got this extra term because of friction. So it's the energy you start with now, right? Which is all gravitational potential energy. You're up here, you're not moving. Yeah, it's still going to give you some kinetic energy down here. You're still going to be moving. But all of the energy would have not gone into velocity. Some of the energy would have gone into velocity, but some of the energy would have gone into heat transfer, thermal energy. So we have to add that. And then we get to the next step. That initial energy is all gravitational potential. The final energy that is conservative part is kinetic. There's motion there at the bottom of the ramp. There's no more height, so there's no more gravitational potential energy. But I can still continue here and put in mgy is equal to half mvf squared, right? And this would equal the magnitude of the force of kinetic friction times the magnitude of the displacement that it went through. And this would equal mgy is equal to a half mvf squared, right? Plus, well, what is the force of kinetic friction? What is the force of kinetic friction? Well, if you take a look here, you can draw a free body diagram on the object as it's falling, right? There would be the force of kinetic friction working against it as it falls. Against the motion, there's the force of gravity, and there's the normal force. And we have to take that force that's gravitational, and we've got to break it down. We've got to break it down into components here. So there's force of gravity y component, because remember, we're using that peculiar reference frame, x hat down the ramp, y hat perpendicular to the ramp. And then this would be force of gravity x component, and we have theta right down in here, which means that we've done this so many times that theta would be right there. Well, you've got to remember that the magnitude of the force of kinetic friction is always equal to mu k times the magnitude of the normal force, the magnitude of the normal force. But I know what the normal force's magnitude is, because if you take a look here, the only forces acting completely in the y-hat direction would be normal force and force of gravity y component, right? Those are the only two acting in the y component. And since the object is not jumping off the ramp or sinking into the ramp, we know that normal force and force of gravity y component have to have the same magnitude, even though they have opposite directions, which would be mu k times the magnitude of force of gravity. Now, force of gravity y component, that would be cos theta. That would be cos theta. So let's put that in there right now. Let's put that in there right now, because that's what we were looking for, force kinetic friction. And we can put in their magnitude, right? We can put them all in the magnitude signs, because look, I still got these two magnitude signs. So everything is magnitude. I don't even need the negative sign here. It's magnitude. So mu k force of gravity cos theta. Negative signs don't really amount to much here. And I still have delta D there. Okay, so now I have mgy is equal to half mass velocity final squared plus magnitude mu k force of gravity cos theta. And now we want to look at delta D. Now we want to look at delta D because that's really important. We want to write delta D in a slightly different way. So if we look at this delta D, it corresponds to this height, excuse me, to this hypotenuse, I should say. So we can put in here H. It's the hypotenuse of the triangle here. It's the hypotenuse of the triangle. So we're expressing it in a slightly different way. And then here we'd have mgy is equal to half mvf squared plus magnitude. Force of gravity is just mg. We know that. Cos theta times this magnitude of the height. Well, lo and behold here, look, mass cancels out everywhere. That's quite convenient. So we have gy equals speed squared, speed final squared over 2. And this is all magnitudes. So as long as I plug in positive values, I don't need to put the magnitude signs anymore. Okay? Don't need to put the magnitude signs anymore. Just have this right there. So if I rearrange this here, I get g times the y, that's the height change, minus mu k g cos theta h, okay, equals vf squared all over 2. So I'm going to multiply both sides by 2, and I get 2 gy minus mu k g cos theta times h is equal to vf squared. Now I'm going to square root both sides. And I get 2 bracket gy minus mu k g cos theta h, close the bracket. Remember, I got brackets here. And that's going to equal final speed squared. Now, let's compare this to when it was without friction. It was just root 2gy, right? So here's your root 2gy, but you're subtracting from it with this other term. So since you're subtracting from it within the square rooting, your final velocity, oops, that's not squared there, I made a boo-boo. Let's get rid of the squared. Since you're subtracting here under the root, you're subtracting a smaller number. So the velocity when there is friction is much smaller. It's smaller, let's put it that way. Depends on the coefficient there, right? Is smaller than when there is no friction. So what I've shown you here is a way to incorporate a new look at the law of conservation of energy, where we keep the original way of looking at it, right? Grade 11. But now we say, look, yeah, some of the energy we had before goes into the energy we had afterwards when we're looking at conservative forces like gravity, but we've got to take care of non-conservative forces like friction. So some of that original energy goes into here, and then we did all the math and free body diagrams and the rest of it, and we proved mathematically, because of the subtraction within the root sign, that this VF is less than the VF without friction. And there you have it. Have a great day. Bye-bye.